now. Okay, so we can start the lecture by reminding ourselves a little bit what we did yesterday. So yesterday we talked about maps, in particular first return maps, and how they can be useful to describe a system that evolves in a nonlinear fashion, especially, and how a very simple map called the logistic map, have a very complex behavior, and how with a very simple equation, due to the nonlinearity, you have these extremely interesting and complex behavior arising from the fact that the expression is inherently nonlinear. So if you iterate the map to discover what happens at several steps in time, you will find out pretty soon that it's very difficult to do it analytically, but it's very easy to do it numerically. And you can observe a very different behavior according to the properties of your map. In particular, this rate of this reproduction rate in a case of a population model. So that's very interesting. That's at least for me. And then we started to kind of try to understand analytically or with some easy mathematical tools the properties of this very peculiar map. And we defined one very important characteristic, which are fixed point. So if this map is going to be stable or not, if it's going to arrive to a certain value and stay there to that value forever, or if it's going to get all over the place and be very difficult, more difficult to treat and understand. And we found out that these properties of this fixed point changes according to the slope, to the derivative of the map at the fixed point, precisely at the fixed point. And for the logistic map in particular, we have two interesting fixed points. One is, now it's saying to me, my connection is unstable. I hope you can hear me well. I don't know why my connection should be unstable. So is it working okay? Yes, I hope it's yes.
I think it cut off for like half a second, but I think it's all right now.
Is anyone else experiencing lag? Okay, so let me know in the chat or by stopping me at the microphone if you are missing some important points. Right now, I'm only summarizing the last lecture. So I was saying that one very important property of the map are fixed points, and you can characterize this fixed point based on the derivatives at the fixed points. In particular, this is due to this very simple analytical expansion that tells you a lot on the properties of this fixed point. And you have basically two types of fixed points, or 2 plus 1. One is an attractor, where the system evolves moving towards the fixed points. If at any given moment in time the system approaches the fixed point, then it will be drawn to it and will reach it most probably asymptotically. Then you have unstable fixed points, where on the other hand, if you are at the fixed point, then it's perfectly fine, you stay at the fixed point. For example, in 0, in the logistic map, if you are at 0, you stay at 0 forever. However, if you have a slight deviation from 0, then the system will evolve in a completely different direction. Then you have undecided, and then an important property are superstable fixed points, where you reach the superstable fixed points in a finite number of steps. And these approaching can be either monotonic, so a proper asymptotical behavior, or alternate, so oscillating above and below the fixed points with a kind of damped oscillation motion. And then we found out the properties of this fixed point for the logistic map, and we found out why we had this very complex behavior, because according to the rate of reproduction R, the fixed point has different properties and different derivatives that are larger or smaller than 1 and positive or negative. So you have all of this. Okay. So I hope this is all clear, because now we will move forward. And one thing that I want to excuse myself is this. I exported in the Canvas and I uploaded in Canvas the PDF of the lecture notes. However, OneNote has a terrible PDF export tool, so it doesn't seem to make us much of a favor. So if any of you knows a better way to do it, please let me know. Okay, so let's start the second lecture. And the second lecture will be also about one-dimensional maps. Probably I can continue on the first page. What do you think? So, is it fine? Yes? Somebody is answering. I hope I'm not killing you in the morning with this, and you can follow without too much problems. So now how we go forward from here? We already arrived at a given point, which is quite interesting, and where we can make interesting consideration about this logistic map in a very simple fashion, just treating the map as an analytical function and then calculating derivatives. So how do we go forward from this? One also quite intuitive thing to do is to look at the how the map evolves in subsequent steps. So now we define the fixed points for the first return map. And this is very easy, very easily seen that you have fixed points in the first return maps. And they have this very definite behavior. But however, you have that some of the behavior is kind of this oscillation across 2 points. So if I increase the R to be greater than 3, I don't have a fixed point in the first return map anymore, because then the fixed point gets to a value larger than 1, and therefore gets outside of our map. So if I don't have fixed points, and how the system will act. And one way to discover how the system will act in this case is where I cannot find easy fixed points. Of course, I still have the fixed point in 0 for every return map, for every value of R, but this does not help my analytical and predictive power much, because I don't want to understand the very trivial situation where nothing happens. So in the case that the system is oscillating 2 by 2, so let's draw it here. So let's draw the case. This is J, and this is X of J. At each and any point in time, the system will evolve. And as I told you, it will evolve exponentially at the beginning, and then it will evolve through other behavior that depends on R. If R is slightly lower than 3, what happens is that I will have this oscillating pattern where I will have 2 viable solutions. And the system will oscillate among these 2 points, simply because the system you will reach to a point where in the logistic map, you will arrive to a point around here where the value is smaller than this point, of course, because the xj is lower and it's below this line. But it will send you to another point here where the value is exactly the first point. So you will start to jump between the 2 points. So if we draw it as a map, so this is xj and xj plus 1, you will arrive to a point so if L is very big.
Andrea?
Yes?
It's a bit hard to see where you're pointing when you say this point and this point.
Yeah, I know. I don't know how to do it in a nice way. You are very right. I also have to get used to it. So let's if you know a way that I can use my pencil as a pointer in one note or in another program, let me know again. But going back a second, so you're right. So the system will oscillate between these 2 points that I'm drawing here.
Yeah.
And then we'll continue to oscillate here and here and here and here. So this will be really not a continuous oscillation because these are discrete steps. This is step j, and this is the step j plus 1. And this is j plus 2, and so on and so forth. So the system will just jump back and forth. I draw the lines because this is convenient, but actually this will be just a set of discrete points. And the line is just to guide the eye. And then you will arrive to a point where the system will jump up and down for each and every step. So this system is not stable, does not have a stable fixed point. But what happens is that if you jump twice, you go back to exactly the same point. So let's add this pen, a yellow one, okay. So you will arrive to exactly the same point.
All right.
Okay.
Thanks.
So what happens in this case? So why is that so? Is because the system has actually a fixed point, but is very unstable. But what does it have is 2 points that are very easy to reach. And what happens is that the value when xj is at the fixed point, now it's very difficult to draw it by hand. Let's see if I can wing it good enough. So if you arrive at the given xj here, then your point in xj plus 1 will be at a lower value respect to the xj. And this lower value will correspond, so this is xj, this is xj plus 1. And this lower value will correspond exactly to the point where the value of the map at that point, so xj plus 2, is again equal to xj. And so the map will go back and forth between these 2 points. This is what generates this sort of behavior when r is slightly larger than 3. And how can I study this? I mean, this is something that I find, maybe analytically, I don't know, and I don't think that this behavior of the logistic map was discovered before its calculation with computer. I'm not super sure, but I think not. But with computer, let's say that you calculate with a computer and you find out that for this r slightly larger than 3, you have this up and down behavior. And this means that you will have a map condition that will do these sort of things. Now, the way to study this is, the intuitive way to study this is the second return map. So we talked about the first return map, but there is nothing stopping us from studying how xj plus 2 behaves in function that I call function 2 because it's a second return in function of xj. If I study this map, I will observe that these two xj's are fixed points in the second return map. Okay? So is it clear qualitatively why? Yes, or maybe not. Yes, there is one yes, but I don't know if it's from before. So let's continue maybe. I don't know. You tell me, is it clear or not? Nobody is answering. Are you alive or dead? Nobody shared the video, so maybe you are doing breakfast and that's fine. But give me a signal that you are alive. Yes, some of you are alive and they like what they see. Okay, so if you have such an oscillating condition between 2 and only 2 points, it means that you have the fixed point in the second return map. Now the fixed points in the second return map are also fixed points of the first return map. Let's establish a way of considering this first, second return map and a notation. So this is called second return map. And then I say that F1 is the first return map, and then I can have Fn, that is the nth. Yeah, let's use lowercase because uppercase, I used it for the population. Nth return map, okay? So you have first, second, third. You can have whatever return map you want. So now our property is that if xj star is stable is a fixed point, let's call it fixed points, because it can be a stable fixed point or unstable, is a fixed point for the first return map, then it will follow that xj star is a fixed point for the second return map, or the nth, to be more mathematical and general. So this is fairly simple to demonstrate using the properties of the derivatives. So if I do the derivative, when I write formula, maybe I should not have activated the shape thingy. Yes, okay. If I write the derivative for the second return map at the fixed point, assuming that the first return map has a fixed point in the same x star, so this is equal to f prime. So yeah, before doing this, maybe let's go by step. I can move this section slightly lower. I don't know why I didn't take the F. Okay, so what is the second return map? Okay, so simply F2 of a given xj is equal to F1 applied twice, okay? I hope it's clear, but let's do it. If you want to do it step by step, this is equal to F1 of xj plus 1, that is equal to xj plus 2. That is exactly the definition of F2. Okay, so now we can go on and study the properties of the derivative. So if 1 is a fixed point for F1, then is a fixed point for any F. And this is also an intuitive property because it's very easy to to understand it. If one point is stable from step 1 to step 2, then it will be stable also from step 2 to step 3, and therefore it's stable also from step 1 to step 3, and so on and so forth. So it's very intuitive and easy. But since these first lectures are also an occasion to get the gist of the course and the topic with something so simple that it might be for you trivial and mathematically trivial, but the idea behind chaos theory and dynamical system is that this is the topic that is a little bit in between, and it's an interdisciplinary topic between physics and mathematics. So it's really something. Yeah, I mean, it's something that you can study either from the physical point of view or the computational point of view, and put a lot of effort into computing the properties of your system and making very nice simulations to describe a very sophisticated system. Or you can also make the point that these are a relatively simple system which have a complex mathematical behavior. And so you can kind of study and go deep into the mathematics to understand these sort of systems. And there are people that do exactly that. So there is a group of people I know, and they study really dynamical system as theorems. So they develop sorts of theorems to approach these type of systems that we will see during the course, and from the physical perspective are quite easy, so couple differential equation. But if you really want to demonstrate what does it mean for this type of system to go into a chaotic regime, then it's really interesting from the mathematical point of view, from the formal point of view, not only from the fact that these systems display a very complicated behavior despite their very simple mathematical formulation. Mathematically, you have to, it's an occasion to sort of go into why a simple mathematical object can display a very complicated behavior. So Johan raised the hand. Fantastic. We are the first raised hand in the course. Do you have a questions or a comment?
Yes. Yeah. I just had a question about the fixed point thing. I think I misunderstood or something. Was it true that a stable fixed point for the first return is always a stable fixed point for the second?
Yes, for the nth.
Okay.
Because of the definition, no? So why does it do this? Okay. Good. So if you take this definition here, you can see it mathematically if you want to be really, really convinced. So if you take the second term map of xj star of the given fixed point, let's drop the j index because it's meaningless. All right, let's keep the xj. So this is equal to the first return map of the first return map of xj star, okay? And this being xj a fixed point, this is equal to the first return map of xj star plus 1. So it will be the next iteration, but the fixed point will be exactly the same. And then this will be x star of j plus 2. The index now only tracks the time, but the value of x star is always the same. And this is true for any nth map.
Yeah, I was mostly wondering about the stability. Is it always a stable fixed point?
Yeah. Sorry. I dismissed your question far too frivolously. And the answer is yes, because here I demonstrated that if it's a fixed point.
I can't see where you're writing.
Yeah. So here, the thing that I'm moving right now, I demonstrated that if it's a fixed point, I don't know why.
There is something wrong with the shared screen. I cannot see that either. Anything that you are writing now, last 2 minutes or so.
Really? Okay, I'm very sorry. You don't see anything? I see my shared screen in the last 2 minutes. So you don't see, so now I'm making a red sign. Do you see it? I also don't see it.
No.
Okay. Very sorry about that. So let's try to stop the sharing and redo the sharing. Stop share. Hello. Redo the sharing. Yesterday, there was the first time worked so flawlessly, and I was very happy. And now I have problems. Okay, interesting. So now you see it?
Now we can see it.
Okay, fantastic. Sorry for this. That's the show, and the show must go on. So if I can move this a little bit lower, I would be very happy. Okay, so now you see that this is the definition of the second return map, and the fact that the second return map basically is equivalent to applying the first return map twice, or the nth return map is equivalent to applying the first return map n times. And this implies that if it's a first is a fixed point for the first, then it's a fixed point for the nth. It is a very intuitive, but mathematically we can study it like this. And also, your question is exactly what I wanted to explain afterwards. So this is quite trivial, I think, I hope. I'm not sure. Is it trivial for you? Yes? No?
This last step, yes.
Let's see the chat. Okay. Very good. And then the Marcus, is not clear also the fact that if you have a fixed point for the first return map is also a fixed point for the second and the nth. So only the thing that I have on the slide right now. This should be clear. Yes, fantastic. And then the stability. That's exactly the thing that I wanted to go further. So this is, you can call it, it's a little bit too small to call it theorem, but let's call it point. Point 1. And then let's go to point 2. So the stability or not stability, so the stability character of fixed points, let's use the notation that we used up to now, of x star for F1 is valid also for Fn, F2, F3, F4. So it's very easy to demonstrate it for F2, and then by you can demonstrate it for a general n by inductive principle. So, but this is by induction. So this is very easy to demonstrate for F2. So we'll do it like this. So the derivative for F2 is equal to the derivative for F1 of F1. Okay, this is because of the definition of the second return map. And this is equal to properties of the yeah, if I should, let's do it rigorously for now, well, the notation for now, and then, so this is the first return map prime, so this is the derivative of the first return map. Times the first return map derivative. So this, I exploit the properties of the derivative, and I take the derivative of the inner argument times the derivative of the outer arguments. So this is for the fixed points. So basically, this is the application of the first vector map to the fixed points that gives the fixed point again. So this is the derivative of the first vector map squared. So this is the derivative of the first return map at the fixed point squared. Okay? So if the absolute value of f prime of the derivative of the first return map is greater than 1, it will continue to be greater than 1 because it will be greater than 1 squared. If it's smaller than 1, it will continue to be smaller than 1 because it's smaller than 1 squared. However, if you have an alternating, so sometimes you have to look also on my screen, so I will do, I'm doing the thing, I hope you see me. So if you have alternating behavior for the first return map, and they go and they make this kind of damped oscillation motion, so they alternate with a kind of smaller and smaller amplitude around the fixed point. So if they have this sort of oscillation, then the square will only take into account the upper ones. Well, of course, maybe it's... So this I could explain it with my hands, but I think you don't see me good enough. So if you have the fixed points here, so this is your X star, then your map can do this sort of behavior. And this is again something that is discrete and I draw as continuous because I'm a very poor drawer. So this is jumping up and down. So this is the sorts of behavior that you have for f, yeah, you can write it, f prime, f1 prime of x star smaller than 0, but greater than -1. So the fixed point x star is a stable fixed point, but is a stable fixed point because the absolute value of the f prime is lesser than 1, but it's this alternative behavior. But then f2 prime of x star will be greater than 0 because will be the derivative of the first return map squared. So it will be greater than 0, but still lesser than 1. So it will be still stable, but kind of approaching it monotonically. And this is true because according to what number you pick, let's use the blue. If we do the second return map, this will be 1 every 2. So it will be like this, and then here, and then here, and then here, and then here. So we approach the fixed point monotonically in a stable way. And if you have f3 prime, these preserve the sign. So this is again -1, 0. So it's lesser than 0, so it will be alternating. And you can see this, let's do it in green. So if we start at the same, you will see 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, sorry. I'm so crap in the morning that I cannot even count 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on and so forth. So you see that for the green one, for the green one, I have, sorry, I have this alternative behavior once again. Okay, I hope it's clear. So this is all pretty intuitive, but it can easily be demonstrated mathematically, this behavior. Okay? Very good. Okay. So I think I said all I wanted to say about first, second, and third map, and I hope it's clear, so I can go on with the other topics of the lecture. Do you have any question regarding this part? I've opened the chat.
Yes, I have a question. So if you had a map which has an oscillating behavior with 2 fixed points, how would you find those 2 fixed points?
By calculating the second return map. So this is exactly how you find it. And then you find exactly as you did before by making an equivalence like this. But here you will have the second return map. In the case of the logistic function, you have this. So this is also your second return map. And then you can study the stability by solving this equation equal to x star for substituting x0 with an x star, and then studying this equation here that I'm indicating with the arrows. You go on and you study the value of this equation for a stable point. So you substitute all the x0 with x stars. And it's not as easy, it's true, but for such a simple case, this is still feasible analytically. However, it's true that when you go for higher return maps and when you go for more complicated maps, then it gets much complicated very fast. So in a few steps, my connection is unstable again. I hope you heard me. So as I was saying, you can do the same that you did before, but with the second return map. So kind of studying the stability by fixing an x star, just like you did here, but using the second return map instead. And this is feasible analytically for the second return map for such a simple case like a logistic function, but gets very messy very quickly. And so it's true that it can get very complicated. And this is why you have to help your intuition with the numerical modeling of any nonlinear system, because the system gets very complicated very quickly. So if you want to find 3 periodic or 4 periodic solution to even to the logistic map, it's really difficult. It starts to be a nightmare. It's not impossible again. And now with the modern tools like Mathematica, you can do it, I think, for such a simple case, but even Mathematica struggles if you have maps that are slightly more complicated and you want to study higher return maps. So is it clear?
Yes, thank you.
I will not do it because it's just an algebraic exercise and it's very long and boring. It does not give you any particular insight. But one important thing is that now we have all the instruments to study the properties of this logistic map. So I want to share my screen. New share of, let's see, preview chaos text. Okay. Now you should see the text. So
it's not really moving for us.
It's not working for you?
No, it's not moving.
So it's not moving.
Table of contents.
Okay. Okay, that's a bit of a bummer. But let's do like this. Because I paused for some reason. But okay, then let's use the iPad for a second more. Since it gets so boring. So now we can go and start to studying the properties of this logistic function in what is called a bisection graph of logistic map. Sorry, I said function, but it's a map. Are two different things. So if I make a graph very big here, okay, and I study the behavior of the stable points, of the fixed points in function of R. So I remind you, the logistic map looks like this. F of x is equal to R of x, R of x times 1 minus x. Okay, so I want to study for fixed points. What is the value of the fixed point for this logistic map? And for a very small r, for 0, of course, the only fixed point is 0. For a small r, then the fixed point increases because. So let's use also this piece of real estate. It's very difficult to show you on this case. I will use my body, but I hope it's clear nonetheless. So if I draw the logistic map here, and the R is very small, what it means is that the fixed point is very close to 0. If the R is slightly larger, so let's use this other color. So if the R is slightly larger, the fixed points will be higher, and so on and so forth. So the larger it is my R, the higher it goes the fixed point at the beginning. It will still be a stable fixed point with all the nice properties that we makes this very well behaved, and it will increase, and will increase in this way. So R will increase more and more with a stable fixed point for some time until, as I say, R is smaller than. If I do it like this, I will not have real estate. So we calculated. Oh my God. Okay, good. We calculated some interesting 2, 3, 4. So we calculated some interesting points where interesting stuff start to happen. So when my R is smaller than 1, what happens is that it stays to 0. Okay, because the only fixed point I will have for a truly small R, I will have that the logistic map always stays below the section line. So for r smaller than 1. For r greater than 1, I start to, and I have this regime of decay. So you can, I hope you can see me now. So these were the regimes that I had, and I anticipated you at the very first hour of the first lecture. For r smaller than 1, I have this going down. For r greater than 1, this goes up and forms a logistic function that rises exponentially and then plateaus. And then you have oscillations that are quite interesting. So at first, you have this behavior that r starts to raise up, and this is still a kind of well-behaved, stable fixed point. Then you have a stable fixed point that, however, is approached with alternation. So you have this splitting of the solution, and the fixed point is still 1, but you have it going up and down the fixed point for r between 2 and 3. But when you have r equal to 3, some magic happens. So what happens is that you don't have one stable fixed point anymore, but you have 2. And you have this bouncing up and down solution. Tack, like this. And then, for a number that is greater, you will have the splitting of this. For a number that is greater than 3, you will have a splitting of the fixed point into 2 fixed points that will be fixed points for the second vector map. However, so this is kind of a liberty that we take in the notation. However, the solution will be oscillating between 2 points. And so I represent it this way. And this is called bisection or bifurcation, because your solution bifurcates, splits into 2. And then you have again another splitting of your solution. And then you have, for smaller and smaller values, splittings of solutions. And pretty soon, you will reach a point where you have a system that is oscillating among many, many, many solutions, and you cannot track anymore and your system does not behave anymore as any sort of periodic system. Will not oscillate among given number of solutions, but the number of solutions will be so large, if you will, that will make basically a continuum of solution, and the system will jump across the board. And this regime is called chaotic. So a more proper representation of this graph is this. So this is an enlargement of only the bifurcation part. I will find out one at higher resolution during the break. But this is the idea. So the first part of the graph goes as we did before, and then at 3, you start having this bifurcation that are more and more frequent. And if you zoom between 3 and 4, you will have something like this. The funny thing is that after this period in between, that is called a chaotic motion, because you don't have any sort of periodic behavior, you will have a system that will oscillate among 3 solutions. So this is kind of a very unexpected thing. And the period doubling cascade, how is it called? Because it will double and double each in a smaller step of R, for smaller and smaller R steps, will be interrupted by this solution, by this regime in which the solution will be 3 periodic, in a sense, with probably some noise. And we will see it after the break. So it will get a little bit more qualitative right now, after the break. So we can take a break now for, let's do let's do 10 minutes and then we will meet here once. I see you have questions, but let's try to do this since I am slightly below. If you discuss with your colleagues over the break, then we can kind of we can come back from the break with some clear ideas. Okay, I will split you into breakout rooms and will remain here. Good. See you in 10 minutes. Let's stop the recording. Okay, do you have any questions now for me? You had plenty of questions before. Stop share. You had plenty of questions before. You solved it all talking to your colleagues, I guess. Okay. So if you, one new message. Pointer to use it, click, draw, then expand pen, gallery. No. I think so. Okay. So if you have questions or you feel that like you want to comment or not understand something, or if you don't hear me correctly, just please talk right away or raise your hands or write in chat, but let me know. Don't be afraid of asking any sort of questions. Questions open up possibilities. So let's share my iPad screen. If you don't have further question, I will go on and explain. Okay. So I will go on to explain the Lyapunov exponent. So, and other properties that we can now study of this bisection or bifurcation graph. Yeah, I use bisection for too many. Let's say bifurcation. So you see now my screen, bifurcation. Okay. Very good. So one very important things are now Lyapunov exponent. It is maybe well, I would not say the most important thing about chaos are often used in a non-correct way. But it's the most, it's kind of an hallmark. And if you see Lyapunov exponents is kind of an easy number that tells you how much your solutions are diverging one to another. So how much your system is chaotic. I explained in the first lecture, I mentioned this property of sensitivity from initial conditions. So when you get on the right of this bifurcation graph, and you have plenty of bifurcations, and you go into a regime that is called chaotic regime. And in the chaotic regime, you don't have any periodic solution. You just have fairly interesting behavior that is absolutely non-periodic, and it seems almost random, but as we've seen, it has some structure, because you can see that you can get out of this chaotic behavior, and this would not really happen if it weren't structured. So if this feature were not structured. In fact, chaos, why does it appear? So I asked not to appear, but okay. So in fact, chaos is something which has an inherent structure that might look random, but there is an inherent structure behind, and is this inherent structure that we can study. We cannot predict in any way the properties of a chaotic system. Well, sorry. I'm now distracted by the fact that this notation starts to appear, and I put in the settings of the iPad not to show notations, but okay. So one important feature of chaos is that you have some inherent structure, and these properties of this inherent structure is the thing that you can study. However, you cannot, or it's extremely difficult to predict the precise point that the system will have in the future. What will be, for example, the population in the future if the population can be modeled by the logistic map. You can predict for a few steps, and despite the fact that the system is completely deterministic, once you have a number, then you can follow the evolution of this number up to any precision you would like, and it will completely follow in a deterministic fashion. If you start from exactly the same point, you get exactly the same result. But a small deviation from the starting point will imply that your system will evolve in a completely different fashion, in a completely different way. And this is called sensitivity to initial conditions. And it's shortened often in this context as SIC, SIC. Sensitivity to initial condition exactly express this property of having solutions that are extremely close to each other but diverge in an exponential way. And the Lyapunov exponent is the exponent of this exponential, of how two solutions diverge in the future. So this is an hallmark of sensitivity to initial condition. It's not enough to define chaos, because you can have very easily solutions that diverge exponentially. For example, for the linear map that determine exponential solution. So if you have a slightly different at the beginning exponential, the difference among the solution will diverge exponentially. But this is not chaotic system. So it's not enough to have a positive Lyapunov exponent to say, okay, this system is chaotic because it has sensitivity to initial condition, but is extremely good indicator. Because very few systems display this sensitivity, if not through chaos. Okay. So how can we mathematically formalize what I just said? So I want to study solution with a small difference. So let's say that in my map, let's use this draft. So let's say that in my map, I start from here, or I start from a very close point here. So this would be x and x0 and x0 tilde. So these 2 points start extremely close by. So we have 2 points, x of j and x of j tilde, that are extremely close by at the starting point. So we have a x0 minus x0 tilde. At the starting point, I start with 2 different points, and this is much smaller than 1. So if the maximum value x0 can have, x0 minus x0 tilde is very, very much smaller than 1 in a mathematical sense. However, it's also greater than 0, strictly greater than 0, of course. So there are 2 different points that can be infinitesimally close, but still there are 2 different starting points. How the solution will diverge? So I define delta x of j as the difference between this x0 and x0 tilde. I can consider the absolute value or not, but this does not matter that much. And let's consider how, if I have a certain point in xj, how xj plus 1, the absolute value, will evolve respect to xj. So xj plus 1 is simply, the absolute value of xj plus 1 is simply xj plus 1 minus the absolute value of j plus 1 minus xj plus 1 tilde. And this is exactly the same as f of xj minus f of xj tilde. Okay, despite one thing that I forgot to mention is that before here I define the first vector map with a 1 on the top or a 2 for the second vector map and so on, when I don't put any other symbol. So these are first vector map because bring you from xj to xj plus 1. Strictly speaking, these are first vector map and can be noted like this. But when I omit the ones on top, let's see if I can delete in a surgical fashion. Fantastic. So when I omit the ones on top, it's basically like this. Okay, so if I consider this behavior, again, I can use the same approximation that I used before. So this is roughly, well, it's at first approximation equal to f prime of one of the xj's, either xj or xj plus 1, times delta xj. Okay? So, therefore, if yeah, this is like we've seen before, in the same way, an f prime negative at the fixed point determines that the fixed point, sorry, not an f prime negative, an modulus, an absolute value of the derivative of the map at the fixed point determines that the fixed point is an attractor. In the same way, the derivative of the map at any given point, if it's less than 1, determines that this delta xj will get smaller and smaller. So will tend to 0 for j that goes to infinity. Okay? So these cannot make sensitivity to initial condition, because if I start from 2 points which are slightly one close to the other, they will approach one to the other. So this is definitely the opposite thing with respect to sensitivity to initial condition. However, if I have an f prime at any given point xj greater than 1, then delta xj will grow and grow. Let's say we get much larger. Where is it? So it will get, let's write it like this, because I don't want to write infinity corresponding to j, because to x, because I define x as between 0 and 1. So the xj will grow much larger than x0 for j, for big j's. So the more I iterate, the more these two solutions will diverge. Okay, so in this case, actually, in the same way that I did before, delta xj, the absolute value, will be given by yeah. So will be roughly equal to f prime xj to the power of x, sorry. Yeah, I can use xj to the power of j times the absolute value of delta x0. So this is an expansion and determines that the solution not only grow apart, but grow apart exponentially with a factor step by step at each and every j step. So if we consider the delta x, since the point is completely arbitrary, I can choose as one of the xj the fixed points. So this is also a way of writing it. So let's say that after okay, yeah, let's do it a little bit slower. Let's not rush through it. So now I will define, for simplicity, the fact that xj, I will pick one of the two. So I will pick xj to be the fixed point. So in this way, it's very easy to iterate iteration after iteration, and I don't have any ambiguity on what point should I consider the derivative of, because xj continues to change iteration after iteration. So this will span different derivatives. But if I pick the fixed point, then this solution is f prime at the fixed point continues to be fixed iteration after iteration, while the point slightly away from the fixed point, if f prime is greater than 1, will diverge and will grow apart from the fixed point. So delta x, and I call this of n, and I call this of n, that is equal to x tilde of n minus the fixed point, the position of the fixed point. So I will pick at position 0, at time 0, and x tilde that is slightly away from the fixed point and the fixed point, and calculate how this difference evolves. So I don't know why I don't see the chat anymore, or any of you. Where is the chat? I don't know. More chat. Okay. Very good. Nobody has anything against this. So if I do this, then I can calculate this as the f prime at the fixed point power of n times the delta of x0, again absolute value. And this is equal to delta of x0 absolute value times, I can rewrite this as an exponential in this way, n times the logarithm of f prime x star absolute value. Okay, just using the properties of the logarithms and the exponential. So I can define this as the Lyapunov exponent, lambda. Okay, and then therefore this is equal to the absolute value of delta x0 times a to the lambda n. So if lambda is greater than 1, this will grow apart very rapidly. So this means that what I'm interested into is this lambda, because defines the rate of separation of two solutions. And in this case, I defined it close to the fixed point. But this is kind of a general property of the map itself. I can pick whatever point, and lambda will be approximately the same. Of course, lambda needs to be, for most maps, needs to be calculated numerically. And since in most practical application, your solution are also calculated numerically, and lambda is an exponential, that's not trivial to calculate because these quantities grow apart very, very fast. And the numerical precision, it's for this type of calculation extremely important. So you have to manage your numerical precision in a way that can be computationally non-trivial, but really depends on the system that you want to describe. You can, in some cases, and probably will not see it today, even though I plan to see it today, in the case of the tent map, for example, one can define a map where this lambda can be easily calculated analytically, and then you can study the chaos in its simplest form, let's say. But even for the logistic map, this lambda is not easy to calculate analytically once you are in the chaotic regime, because the chaotic regime is defined precisely by the fact that you cannot compute it analytically in an easy fashion, so you have to compute it numerically, so you have to compute the properties as well, and the derivative of the map in some given point as well numerically. And this is not easy to do, but is of course possible. So finally, I can define in a more rigorous fashion the Lyapunov exponent as the average value of this. So the proper definition is to take the average value of this growth rate. So taking the limits for very large n, for n that goes to infinity, and then normalizing by n, because otherwise the system grows to numbers which are not between 0 and 1. So this is the limit, is a double limit. So mathematician can have fun to demonstrate how this double limit is analytically sound. So how can you exchange the two factors in the double limit? So this is the limit of the logarithm of, here I defined the derivative, but in a numerical way, in a useful way. The way that I can define also this is by inverting, here I define the logarithm in as the absolute value of the derivative, the logarithm, here I define the Lyapunov exponent as the absolute value of the logarithm, and here I can also define the Lyapunov exponent by inverting this relation, by considering the two delta x. In this way, it's better to calculate it numerically because I have this simple recipe that can be numerically applied. Then the stability of this recipe is another deal. The computational stability of this recipe is not trivial, but it's way more stable to calculate it as a ratio of this delta j, of this delta x. And this is like this. Okay, so this is the definition of the Lyapunov exponent. And if you take this limit in their analytical sense, you can also see that this corresponds to the derivative of the nth map of x0. So that corresponds to the derivative of the first vector map in xn. And yeah, so this is corresponds to the derivative of the first vector map of x of a given xn. So this can be also used in this other way, but computationally is usually more useful the other way around. So, sorry. Let's do it in a more rigorous fashion in this other way. So the derivative of this Fn corresponds to the product for j that goes from 0 to n minus 1 of f prime of xj. That also is related to the derivative in xn, but the idea is to iterate the one that we derived at the beginning of the lecture in this way. So this is the second, as you can see, this is the product of the f prime. In the case of fixed point, is like this. And if you iterate this for the third return map, in the case of fixed point, will be this one to the third, like I explained before. And this is due to the fact that you have here the fixed point that stays the same for each and every iteration. But in this case, you have kind of an average. And therefore, this is written like this. And the Lyapunov exponent can be computed in this other way. So if I put here this product, f prime of xj, yes, and the absolute value like this. And then this is the limit for n that goes to infinity, 1 over n. And then I can substitute the logarithm of the product with the sums of the logarithms, finally obtaining what I meant to do in a single step. That was probably too large to grasp. F prime, let's do it in a new line. Okay. Limit for n that goes to infinity of 1 over n of the sum, because I rewrite the product of the logarithm as the sum of the logarithms, minus 1, the logarithm of the absolute value of n prime, f prime xj. Okay. Good. And just to summarize, if lambda is the Lyapunov exponent, this is equal to the Lyapunov exponent lambda, then you have an attractor. And if lambda is greater than 0, then you have a unstable point, unstable situation that can be either periodic or aperiodic. In the case that you have an aperiodic behavior, usually this means that it's chaotic. For the maps, this means that it's chaotic. Okay. And good. So do you have questions? Probably you have plenty of questions or points, because I went a little bit faster than usual, but maybe this was okay for you. No raised hand? Did I kill you? Was it clear enough? Yes? Johan, Marcus? Okay. Yeah, don't be afraid to stop me if you don't understand something. If it's so clear, then I'm worried that either you're not understanding or it's too fast or it's too slow. I could go faster. I mean, if you...
I have a question.
Yeah, fantastic.
I think maybe I missed when you started that part. In the last limit of the Lyapunov exponent, which x...
This one?
Yeah, which xj's is that?
So these are xj's that you calculate for whatever, in whatever point. So the thing is that I derived here the Lyapunov exponent close to the fixed point, but the problem is that when the system is chaotic, you don't really have a fixed point. So the only thing, but that's where the Lyapunov exponent is interesting. So the only thing that you can do is taking an average over a number of iterations. And this is what the xj means, or the n means. So the n is for very large number of iterations. So you go through the system and you kind of let it evolve in a in independent fashion, and you track two solutions. And you, for very, very large number of iterations, then you measure the difference of these, how it grows. And then you do this limit, and that's fine. But we've seen with this demonstration, very quick and very quick and maybe a little bit dirty demonstration, we've seen that doing these correspond of tracking the iteration one by one. So you can either do that you take two solutions and then you let it evolve for a long time, and then you track how the differences grows, or at each and every step, you calculate the derivative of your map at that precise step. And then you do this logarithm and you sum, and you do an average over these points that you tracked.
Okay, so this is only possible numerically then?
That's only possible numerically, exactly.
Okay. I think I understand.
Because you have to take these limits, and then you cannot do really analytically, because these limits don't mean much analytically. It's not, since your system is aperiodic, then it's not that you will have a fixed solution after an infinite number of steps. So you have to really track it step by step. And in this way, you transform a kind of one-shot calculation that has a lot of uncertainty numerically in a step-by-step calculation when you track an average, sort of. So you kind of spread the numerical uncertainties you have in an n number calculation. So this is more useful numerically than the first one. Okay? Other questions? Give me questions. No other questions. So I will just show.
I might have just another one.
Yes.
When you said the negative Lyapunov exponent means attractor.
Yeah.
What does that mean?
What does that mean? That's a good point. So that means if you calculate the Lyapunov exponent at a fixed point, and in the case that this lambda is negative, you will have a fixed point, then it's very easy to see why. So it means that that fixed point is an attractor, right?
Yeah.
But if you calculate an average, as I suggested, what does it mean is that that particular map as an attractor, and the two different solutions that you picked initially are converging towards that attractor, in a sense. So that's what it means. And if you track the two solutions exactly in the same way as you do for the chaotic system, you will see the two solutions getting closer and closer together, and the derivative also getting more and more stable, because it approaches the derivative at a fixed point. And basically, that's it. This is what it means. I don't know why it's not opening. Ah, yeah, no, it's open. Good. Is it clear? Is it, or clearer, at least?
Yeah.
So to make it even more clear, let's share at page 35 of the book. It's shown this, the bifurcation diagram and the Lyapunov exponent for this logistic map. So you see that for a different R, so these are different R's, and this graph below is the Lyapunov exponent, and the graph above are the solution of the fixed point. So this very famous bifurcation diagram. So if you take the solution where it was here, that was very stable, approaching one fixed point, the Lyapunov exponent was negative, was very trivially negative. If you go through the bifurcation, then you have this two periodic solution, and it goes up and down in the same two periods. So what happens in this case is that you don't have a proper, you don't have the attractor in the sense of a single fixed point, but you have a stable solution that is simply stable because it's oscillating among two solutions. So the Lyapunov exponent that was this limit here, you calculate the derivative, and the derivative will be always the same, two numbers, but you are now dividing it by the number of iterations that you're taking. So you will get more and more a definite negative value. So we'll just jump up and down these two solution, okay? And, sorry. But then when the system will go into this chaotic regime, which is, as you can see, is pretty soon in the R space, the Lyapunov exponent will start to be positive. And then you will have some regimes, some specific value of R where the Lyapunov exponent is positive, indicating this chaotic condition, in this case of the logistic map. But you will have that for some brief periods, it will start to be negative again. And this corresponds to this three periodic behavior. Here you have this three periodic behavior, and the Lyapunov exponent goes negative. So, and this again, because you're kind of making the average of three derivatives, each of those are negative, so you will have the sum. Well, each of those, sorry, the absolute value is lesser than one, so the logarithm will be negative, so you are making the average among of the sum of three negative numbers. And this is what you get. And in this case, among two negative numbers or four negative numbers, so you will have these brief negative Lyapunov exponent points. Okay. So I think I'm not making in time to do anything else. I'm of course open for questions, but before the question time, I was only to flash this part that we will see the next lecture. So in this part, you can see that the bifurcation gets more and more frequent. But the funny thing is that the ratio between two consecutive bifurcation, so this is one bifurcation and this value of R, this is another bifurcation of this value of 2. So the distance between these, so R2 minus R1, and the distance between R3 minus R2, the ratio between these two values is basically constant. It's not exactly constant, but basically constant. It will approach a constant value. And what does this mean is that this bifurcation diagram is self-similar. So if you zoom in on one section of it, so if you zoom in only on this part, so let's see if we can do it, it will just, here you are limited by the resolution, but it will just look alike the section that you had before. So that's this another Lyapunov exponent diagram with more points. And let's see, I thought that there was, no, there isn't a more clear diagram. But you have this, I will make it by next lecture. You have this universality, is called behavior, that you have these self-similar attributes that we repeat over and over. And this will also lead us to our next topic, that is fractal. So I'm running a little bit late respect to the program. So in the program, next lecture will be fractals, but we will do half a lecture still on this, on maps, because it's very important. My worry is that you really understand very clearly maps. So with this, do you have any further questions?
I still don't have access to Canvas. Is that still coming?
Okay. Do you have other physics questions?
No.
Before going to Canvas? Does anybody has any physics question? If not, then I will stop the recording.